Hello everyone, welcome back to Calculus BC. We're in lesson number 35 now, where we're talking about improper integrals. In this video, you guys can see the two examples we're going to be doing where we're integrating from negative infinity to positive infinity. Right here is our solution. This is what we're going to end up doing. We're going to split this up into two different limits, two different integrals, where we start out with negative infinity going to 0 and then 0 to positive infinity. I also want to make sure that we're clear that we want to make sure that 0 is defined in both these functions, as they will be. In the next video, we'll talk about what happens when 0 is not defined. All right, so let's go ahead and do this problem. The limit as c approaches negative infinity, and then we're going to go from 0 to c, and then we're just going to recopy our function down. So x squared plus 4 dx. And then we're going to do plus the limit as d approaches positive infinity of 0 to d. And again, whatever letters you guys choose, I'm just going through the alphabet with this lesson. So I started with A and B in the first video. I'm going to do C and D here. So there we go. Now, what we do now is what we did in the very first video. So we're going to evaluate this, and then solve them. Now, we're going to integrate our function. We're going to integrate our x over x squared plus 4. So we're going to do that with u sub. So u is going to be equal to x squared plus 4. Our du is going to be 2x dx. So we have to pull out a 1/2 du x dx. So let's keep going with the problem, and we're going to do the limit. And the beautiful thing is we've integrated the same function, so we can do this for both methods, right? So c approaches negative infinity. And so we are left with a 1/2, the integration of, in this case, 1 over the square root of u du. I'm leaving these alone for a second because I don't want to change my bounds. So I will remember to come back and do this a little bit later on. And then we do the limit as d approaches infinity. Again, the integration of 1 over the square root of u du. So again, I'm not putting the c in the 0 and the 0 and d, because I'm going to just integrate this and then change my bounds back. So I don't need to worry about that. Or at least that's what I'm going to say. So the limit as c approaches negative 1/2. Oh, and I really just realized one thing about this. I did forget about the 1/2 here as well. So let me go ahead and put that 1/2 in there. Because I'm going to go ahead and pull out the 1/2. Go ahead and pull out the 1/2 for all of this. So the 1/2 come out for both of those. So if I integrate 1 over the square root of u, so the integration of 1 over the square root of u, well, really it's just going to be u to the negative 1/2 du, which is going to be u to the 1/2 all over 1/2, which is just really 2. So this is going to end up being 2, and then the square root of u. Well, the square root of u is going to be x squared plus 4. Evaluate it from c to 0. And I'm going to do the same thing with this one over here. So this is going to end up being plus the limit as d approaches infinity. Again, integration of 1 over square root of u is going to be 2 times the square root of u, but again, our u is going to be x squared plus 4. And this time we're going to evaluate it from 0 to d. Now, one thing I'm going to say about this problem is this. When we start plugging in, so I'm going to plug in 0 first, and I'm going to get 2, well, again, I get the 1/2. I get 2 square root of 4 minus 2 square root. When I plug in negative infinity here, negative infinity squared is positive infinity plus 4 positive infinity. This is going to be infinity. This is going to be infinity. This is going to let my function diverge. My answer cannot have infinity in it. It cannot be infinity. So I was talking about this at the end of the first video. So anytime you guys get something and you evaluate, and you're looking at the evaluation for it, you get this right here, it's going to diverge. Because this is not a number. 2 times infinity is not a number we can actually calculate. We're looking for an actual answer here. So this is going to be a problem that diverges. So let's look at an example that will not diverge. So I'm going to keep this up for you guys can see it. But for this one, we're going to look at the limit. And I always, always go with x, but I'm going to try to keep it constant here with the letter e. So e approaches negative infinity of our integration of our e to 0 of our function. And most of these are if they're free response questions, then yeah, you want to show all this work for these problems. F approaches positive infinity of 0 to f of 1 over x squared plus 2x plus 5 dx. And just because it bothers me, I'm going to make that actually look like a 1. I think I was trying to look at the f when I was doing that. So let's integrate this. So just like before, this is going to be a completion of square. So if we integrate this problem, we're going to get 1 over, it's going to be x squared plus 2x plus blank plus 5 minus blank dx. So this is a problem that we have to complete the square. So we're going to put a 1 here, we're going to put a 1 here. So we're going to be left with the integration of 1 over x plus 1 squared plus 4 dx. And so we've talked about this before in the previous lesson. This is an arctangent problem. This is an arctangent problem. So really quick refresher on this. U squared is going to be x plus 1 squared. A squared is going to be 4. U is going to be equal to x plus 1. A is going to be equal to 2. And the du would be equal to 1, but that doesn't really matter for this particular problem. So when we do this integration, this is going to end up being 1/2 arctangent of x plus 1 all over 2. Okay, so that's going to be the integration for that particular problem. And we're going to do the limit as e approaches negative infinity, and we're going to evaluate that from e to 0. So actually, let's just do this first part first. We're going to start evaluating this. So I'm going to do 1/2 the arctangent. We're going to plug in 0. We're going to get 1/2. And then we're going to do minus 1/2 the arctangent of, so infinity, negative infinity, plus 1 over 2 is going to be negative infinity. It's going to be a huge number, right? Negative infinity plus 1 over 2 is negative infinity. So that's going to be our first part. And then I'm going to go ahead and do, and we'll talk about this in 1 second. The same thing with this one. So this is going to be the limit as f approaches infinity of 1/2 the arctangent. I'm running out of room here, so I apologize. X plus 1 all over 2, and we're going to evaluate this from 0 to f. 0 to f. So with that being said, we're going to do plus, let's just do it right here, plus. So we're going to plug in f first. So 1/2 arctangent of positive infinity plus 1 over 2 is still positive infinity, minus 1/2 arctangent of, again, 1/2. Right, we're going to plug in 0 to get the 1/2. So you guys can see that these are going to cancel out. So this right here cancels out with this. And by the way, this is still a number. So if they didn't cancel out, that's still a legit answer, right? You can use your calculator to figure out what the arctangent of 1/2 is. It's just not a unit circle value. Now you may want to think that these cancel out with each other, but they do not, because you're taking the arctangent of negative pi. And so we actually have this from the first video. I have not erased it. So if I look at, as we're approaching, this is the arctangent from negative infinity, that value is actually going to be negative pi over 2. And from positive infinity, it's actually going to be pi over 2. So if I come back down here to my problem set, I can see that this piece is going to be negative 1/2 times negative pi over 2. And this is going to be plus 1/2 times pi over 2. So we're going to have pi over 4 plus pi over 4, which is going to give us our answer of pi over 2. So I hope that helps. I hope that makes sense. And I'm going to see you guys in the next video where we talk about more improper integral problems.